All right. Good. So here we are. This is not much left to this. Got today and 2 more classes, and that's it. Next class is canceled. I'll be in China, and then there's the final exam that's just online. So we'll do chapter 16 and 17 today. Just 2 more yet to go. And here's the scores. Several people have already finished with the green, and a few have already got a B with the yellow. But there's still several weeks for people that are still working on things. So we're here. And this is a short couple of chapters about vulnerability discovery. And I'm going to tell you the general principles as far as actually finding new bugs. None of my students has succeeded in doing that yet with these tools. I think the simple fuzzing hit its big victories like 8 or 10 years ago. And the simple fuzzers no longer find anything. And you'd probably have to go to older code or more sloppily written code than normal for the simple fuzzers to work anymore. Anyway, this is a really old technique, putting in fault injection. It's been around for electrical engineering for years, even before computers. You put in faults just to see if your circuit can handle them. And this is part of quality assurance. You have a quality testing in your manufacturing process to see if something is too weak to be sent, and they also use reverse engineering and source code auditing, where you try to figure out how the thing works and find flaws in it. So the design overview is like this. So for computer fuzzing and network fuzzing, which is the most common type, you have a client down here that is generating network traffic, and then you sniff the network traffic. And then you have an auditor who takes the network traffic and modifies it in some way. Simple ways to just flip random bits, make fields longer, add special characters, and so on. They create these modified engines, and then they inject that junk into the server and see if it crashes. And that's the game. I know one of the most famous cases of this was about 8 years ago. Dave Kennedy, who was for a while the Fox News cybersecurity expert, he found a 0-day in the Apple Mac Wi-Fi adapter on the MacBook. And he brought a new MacBook to DEF CON and set it there, and he played a video of the process because he didn't want to leak it. He told Apple, but he did it with 3 computers. He had the Mac that's being tested. He had I think he might have had 4 computers. He had a Mac being tested. He had one machine just sending random packets to the Mac. He had another machine recording the packets over the air with Wireshark. And he had one of these machines was pinging the Mac just to see when it quit answering a ping. And after a while, it would quit answering a ping. He said he let it go overnight. And then you just go back to the captured packets and figure out which packets are near the time when it crashed and play them more slowly to find out which packet crashed it. And he was able to crash the Mac. And he submitted this vulnerability to Apple, and Apple lied. They said he had faked it, he had modified the hardware, it wasn't real, and they tried to drum him out of the business and ruin his reputation. And then coincidentally, they had a patch to their Wi-Fi driver the next week. So it was, and that's the way everyone used to be. Microsoft and Cisco were that way 10 years ago. They would just lie, deny vulnerabilities, tell you to shut up and go away. Microsoft, they've all reformed now. Even Apple has reformed. But this is the early, that was a couple of years before Apple ever admitted they had any security problems at all. At that time, Apple had an official website to sell their products saying, we have no malware at all. And it was a couple of years before they blocked a PDF update that got malware. And they tried to continue to lie and say they had no malware for a while. They told their customer service reps, they sent them instructions saying, if a customer calls and they say they're infected by this known Mac malware, tell them they can't be infected, there's no malware on the Mac, and just hang up on them. And one of the reps leaked that to the press. And that started the outrage that forced Apple to admit that they're no different than everybody else. They have problems, they have malware, they have troubles, they have to patch them. And but I'm not trying to say Apple is more evil than anybody else. Every company did the same thing. They all lied about their vulns as long as possible until they were humiliated publicly so much that they had to admit it, because they would love to pretend they have no security problems. They see that as a high value myth. to propagate about your business. And as far as I can tell, the American banks are still in this place. When I found vulnerabilities in banks, they all came to me secretly. Well, the ones that, most of them didn't respond, but the ones that did respond talked to me secretly at B-sides and said, we can't publicly talk about any of this. And my boss would fire me if there was ever came out that I actually went to B-sides, because that's associating with hackers, and we're pretending we're totally above all that. So anyway, so you have something that puts in input. In general, you'll find interesting flaws if you go for code that's not used much. This is where a lot of the really high value things are, because there's often legacy code that dates from 10 years ago that nobody's ever reviewed. And so this is why there was a scandal about 2 years ago. I think Kimu, or one of the major virtualization softwares, had a buffer overflow of the simple type we've done in this class that would take over cloud machines because it was in the virtual floppy drive. And the software by default attached a virtual floppy drive to every machine, and nobody even remembers or cares about that. And that code has just been sitting there. And of course, it had trivial errors that modern code wouldn't have. So here's one where they're attacking an IIS web server, and for some reason, IIS has some obscure file type called IDA that it does some processing on. And whatever that is, it's the same thing. That code's just been sitting there unused for years, and so it's got old-fashioned vulnerabilities. Here comes a chat message. Let me see what they're saying. Did I miss the 127? This here is the 127, just starting now. All right. Good. Anyway, so the best results supposedly come from manually making your own test cases in a text editor and then setting them up to the device. You can use automated generation. That's what we're going to do here. It's, of course, less efficient, like all automated vulnerability scanning, but more complete. So the simplest way to do it is to start with real traffic and modify it. You could, in fact, try to modify packets on the wire on the way there. That is pretty harsh. That's pretty extreme because, as you know, Ethernet packets are not just simple carriers of data. They have checksums and sequence numbers and stuff like that that you would have to modify. So that's pretty harsh. Anyway, this all started from people using a dial-up modem during a thunderstorm. So they got a lot of defects online, and then they got core dumps. So they discovered that the Linux kernel at that time had faults that you could find with random input that would cause it to crash and dump the core, which is true of everything up through Microsoft Windows Vista. Laurent Gaffey found blue screen of death flaws in Windows Vista. One of the betas came out. He found a blue screen of death flaw, he said, in 10 minutes of fuzzing. And and Microsoft patched it, and they were so upset they released this part of the source code explaining how their procedures, which was source code scanning, did not find it because they run it through a source code scanner, and they look for things like the use of a variable that hasn't got the length being checked and stuff like that, but there was the wrong variable name in one line, and their scanner could not detect that. And so they explained that, and so the next week he fuzzed it again and found another blue screen of death. And he said their whole software development process is garbage. They're just lying about their security and everything. And I don't think that's true. Microsoft said we don't do fuzz testing because fuzz testing is a random process. You never know what it's done. We're more scientific than that. And after they got humiliated twice by Laurent Gaffey, they did add fuzz testing to their regime. So you should do all the other stuff, which is like systematic and logical, and also do fuzz testing because it will find things that those other procedures don't find. Even though it's not perfect at all. It's a random process. You can't possibly try every possible mutated packet. You try some of them, and you hit some of the code, and you find some of the bugs. And someone who fuzzes longer will probably find more, and that's just the way it is. So if you find open source apps, then you can actually add more code to the app to fuzz it, which is much better, of course. Just like when you're debugging something, you put print statements all through it. Now you can put in things that cause it to go to different parts of code to make sure you hit all the code. And I've seen some people that have advanced fuzzers where they actually measure how much of the code you have hit and rate your fuzzing by how much you've done it. The people that develop the theory of fuzzing do that kind of thing. And American Fuzzy Lop is a famous product that does this. So it will help, if you modify the code, it will then put hooks in the code and measure what part of the code is being used and tell you when you have fuzzed it enough. If you have closed source apps, though, like proprietary Microsoft stuff, you don't have this option. You can't modify the source code. So all you can do is send up input data. So you got to have some kind of modification engine. Now, if you're thinking about buffer overflows of the type we started out this class in, then the main thing is to put in large strings where it expects small strings. So you're just trying to make things longer. You can just inject things. So one simple thing, if you have an HTTP request like this that will get index.1, you could try just adding more characters to it. So take some injection string like EI 2003 and just try adding it to each part of this. You can just try adding it to each character location without paying any attention to what it means and see what that does. Or you could just try adding it to the beginning and end of each field, which might make more sense, which might be more efficient, assuming that you probably want to keep the same total number of parameters and the same delimiters. Both of those are pretty obvious ways to test it. Another thing is if you want to make it longer, if you were to try to inject some long string of stuff, you might hit bad characters that are seen as delimiters or filtered out. So a simple thing is to just duplicate the existing characters. Take the first or last character of each data field and repeat it many times. That would be another way to just check for buffer overflows by having long inputs. So if you're delivering your data over the network, the Nagel algorithm is a problem. By default on Windows, small data packets are not sent until they are accumulated, several of them, and they all go together for efficiency. But if you're doing fuzzing, you want to send one packet and have it get there and see if that crashed it. And then send one more and have it get there and see if that crashed it. And you don't really care about efficiency of transferring bytes per second to the server. You want to make sure that each one has been processed before you go to the next one so you know which one made it crash. So you have to turn this off, and there's a flag that you can set to turn it off to make your network less efficient but more precise for this kind of testing. And then you have to have fault monitoring. Somehow you have to detect when you have caused a crash. Now, the Dave Kennedy example from long ago I talked about, he just found that his Mac would no longer answer a ping. So if you're going to kill the whole thing dead, that's easy to detect. But you might have lesser faults that occur. And of course, even if you do kill the whole thing dead, you need more information to exploit it. So you need to run it in a debugger. So you might want to catch every exception also, not just the exceptions that it can't handle. Remember, when exceptions happen, the debugger will catch it, and it will usually pass those on to the application first to see if the application has an error handler. So it'll pop up a message or something, and then only if it has a second error will it usually cause the debugger to stop processing. And you might want to turn that off if you'd like to see bugs, even if there is some code that supposedly handles them, because they might still be exploitable. Anyway, the thing you're looking for mostly is access violations, because those are the ones where you manage to put something in like EAX or EIP that points to an invalid address. That's the most likely exploitable thing. All right. And by the way, there is a module to put in WinDebug called exploitable that Microsoft wrote that will give you a rating of whether this crash was exploitable in Windows operating systems. And there's a fuzzing product from Carnegie Mellon called the fault injection, yeah, FOE, fault observation engine, which I downloaded in previous time I taught this class, and I modified it so it ran on more modern versions of Windows. And one of my students ran it for weeks in the lab trying to find bugs, and we did not find any that we were able to exploit. He found quite a few, but we weren't able to finish the job of exploiting. We didn't really see him finding any new ones. He was hoping he would get his own CVE. Yeah, fault observation engine. Yeah, let me bring it up because I had projects about it. I think I took them out because it just wasn't very successful. But the fault observation engine. The failure observation engine. This is a thing written, and I have a class. I used to be in my project 16 in this class. People set it up and used it. I think I took it out because after a lot of work, we didn't really find anything new with it. Let me see. Yeah, the tutorials down here, which I followed. If you want to do it, you can Google previous versions of this class. I've got instructions how to run it. The original version was from like 2012 or so in Carnegie Mellon, and it did only Windows XP. But I was able to change some simple parameters and make it run against Windows 7. And we tried. Ben spent weeks up in the lab fuzzing a bunch of stuff on Windows 7, and he found some crashes, but he wasn't able to finish exploiting any of them. So it was a lot of work. He was hoping to find his own CVE, but we didn't find it. So I'm afraid if you really want to find a CVE these days, you need to learn to use a modern, complicated fuzzer like Peach or that Fuzzy Lop. And those are all difficult enough to use that I didn't think they were appropriate for projects in this class. It's quite a chore to get them going. Anyway, like I say, I think there was a time when it was very easy to find really exciting stuff with fuzzers, and that time has passed. Now it's hard work to find stuff with fuzzers. That's my impression. Anyway, so static analysis is analyzing code that's not running. You can do the source code, run it through a source code analyzer and look for things like missing format strings and obvious buffer overflows and such. And you can also look in the binary. And if you do that and you find bugs, many of those bugs don't matter, because even if, say, there's a place where something is put into a variable without checking the size of it, it's very likely that what's going in there was automatically generated by another part of the code, and it's never too long anyway. It's only a problem if it's actually data that came from the user. And if you're doing source code or binary analysis, it's very difficult to tell what here came from the user. And that's why fuzzing is a real time saver when it works, because obviously it is caused by something that came in from the outside. Remember, most of the code in an application is not, even if it's vulnerable, it's not exploitable because you can't get to it. All right. So fuzzing is, of course, also scalable. If you write something like an SMTP fuzzer that makes a bunch of modified SMTP packets, you can use it against every email thing in the world without modifying it. It tries, so you can, in that sense, it's saving you time. All right. So here's the weaknesses. Your fuzzing will certainly not hit all the code base. It will only hit the code base you can reach from inputs. And if there's something like a login message or even something that you have to put in a special format to pass, you won't find it. The same thing's true of web vulnerability scanners. You scan, an automated scanner cannot get past a CAPTCHA. It can't get past a login. It can't even get past something that says, you know, put in the social security number with dashes in it or something. It doesn't understand the instructions, so it won't get past pages. It'll miss a bunch of your app. And of course, if you, since it's a random process, you know, random, if you vary 1 bit, there's only 2 choices. If you vary 8-bit, there's 256 choices. If you have 10 parameters that are each 8-bit long, now you've got more choices than you could ever do in the age of the universe. Remember, 128 bits is more than you can ever do. That's why 128-bit cryptography is considered unbreakable. All the computers in the universe running for all the time in the universe will not be able to do 2 to the 128 calculations. So that's not very much. Even that GET request, 128, what you divide by 8, I think that's only 32 bits, 32 bytes, or 16 bytes, 16 bytes. So even that HTTP GET request, if you just decided to modify every byte to every possible value, you don't have enough time to do that at all in the whole universe. So this is why Microsoft originally said, you're wasting your time with fuzzing, this is ridiculous, it's a random process, you're not hitting all the options at all, but apparently it's true that you can hit enough options to find vulns that you're not finding the other way. So, but be aware of it. You can only do a very superficial test with fuzzing unless you are very smart about choosing what to vary. So Spike is a tool that lets you define something called a spike, and then it will put the spike in your data. So it's a simple thing, so easy to use, built-in Kali, so I made a project where you use spike. S-string will insert a literal string in the spike. S-variable will put a whole series of pre-generated automatic strings in here. And S-readline will read a message from the server, because often you have to wait for the server to give you a prompt before you send the message. So here's a spike script. So let me just demonstrate spike. You're going to use it in the project. So if I go to my Windows machine, and this is a domain controller. I think that's not the right Windows machine. Let me start another one. Or maybe it's all right. Let's see. Network error. PuTTY. I don't know. This might work. Let's see if it's got ncat. It does. Okay, so I can do ipconfig. Okay, and I can do ncat -L. Let me get my project up. This project is here projects. Okay. So I can show you the first part of this, so I may need a different target for the next bit. But what I wanted was there, ncat minus VKLP. Okay. That's how you make a listener in Windows. VKLP 9000. Okay, now it's listening on port 9000. All right. And it's listening on that address there, 129. So let's go to my Kali machine. Okay, and first thing I called, let's do, I go to my project instructions. I'll just go with this simple.spk. I should have it. Okay. So this is the simple one. It just sends hello world. That's all it does. So to send it, you use generic send like this. And the only thing I need to adjust is the IP address. My Windows IP address is 129. So, oops, looks like my copy and paste is not working, which tends to happen. I think the defect is mainly Chrome, not copying well. There, where's my Windows machine? There's my Windows machine, all right. There we are. So 170, that looks like that's the right address even. Let's see if it works. Yep, it works. So it's sending a bunch of stuff, and all it's sending in this case is hello world over and over again. Sends hello world, sends hello world, sends hello world. So that's not very intelligent fuzzing. That's just the simplest case where you're not accomplishing anything. So we have to do a little more than that. So we'll make this a variable instead of a string. We'll put this in the spike definition file to run spike again. So that is, actually I've already got it, simple2, there. So if I just send simple2 the same way, now I don't just get repetitive stuff over here, I get their default tests. And their default tests should not be too surprising. You send a whole lot of A's, and then you send some special characters like .. / and so on. They've got a default set of things to try, which are the kind of thing you might reasonably expect to work. All right. And that's the game there. And of course, if you run the vulnerable server and start fuzzing, it will crash immediately on the second input because you already know, I think 3,000 days will crash the vulnerable server with the trun. And here's how you, by the way, you make it start with trun space before it does it. So when you run that, it's going to crash immediately right on the second request. And if you run it, it'll be crashing with AAAA, just the same thing as earlier projects. And you can use Wireshark to see the traffic if you like. And you'll see, of course, the second one is a whole bunch of A's, which makes it crash. So you can find that one, and then you can adjust your fuzzer to start at the next one. You can, to get another crash, you can resume a fuzzing session partway through. So you're starting at 03, you just put that number here. That's what these numbers are in the command line. This says start at case number 3. So you can fuzz until it crashes, and then you can analyze that crash and then resume fuzzing at that one to go forward, because of course, every time you crash it, you have to restart the server. You can't continue fuzzing, it's down. Anyway, that's how you use Spike, which is very easy to use and does this simple fuzzing, and you can see it go. You're just not gonna find anything too exciting anymore with Spike, I think, because everybody else knows how to use Spike, and only people that are really stupid are still making code that will fall for this. Everybody that develops code should at least do this before they ship their stuff. All right, and so that's all I have to show you. Short stuff to cover today. The fuzzer is pretty easy to run. But the really powerful fuzzers are no longer easy to run. And I don't, Peach, for example. Peach is the one people say is great. I've read tutorials. It's sort of mind-boggling. All the tutorials are 200 pages of complicated stuff, and it seems like you pretty much have to be a developer. I couldn't find anything to do with Peach that would fit in the size of one of my projects. So if any of you figure out how to use a real fuzzer, let me know. The only thing I could find close was that Carnegie Mellon thing. That was pretty easy, but it also seemed to only work against code about 10 years old, when just used in its default state. As far as I can tell, fuzzing is not for people that are just taking a first look. It is a research topic, and you have to get into writing your own, customizing your own. You have to be developing a fuzzer to make it work, as far as I can tell. You can't. Now, there are commercial fuzzers. I went to B-side San Francisco about 4 years ago when the iPad 2 was new. And I brought my iPad, which was only like a month old, and there was a commercial Bowne product, one of these ones that cost thousands of dollars, and he ran it right there at the con and found a 0-day and a Bluetooth on the iPad. And I was trying to tweet it when he said, oh no, my boss will fire me if we insult Apple. We can't tell anybody. I'm like, but apparently there are commercial fuzzers you can buy that work for big money. I've never used those, of course. But I think that's what people who develop hardware and software use. They pay for a real commercial fuzzer, where somebody has put in all the work to add this stuff, like a Bowne scanner. I'm not aware of an open source fuzzer that is easy to use and powerful. If you find one, let me know. I would like to have a project where you play with one that, or we go up to find real new CVEs, but so far I've not been able to do that. I should kick this guy out. I don't know what kind of, there should be some standards to who we let in this class. DVD, common vulnerabilities and exposures. It is the list of known vulnerabilities that are verified and which people then write articles about, patches for and such. So it means you found something new. Everything we study is old. It's already a known CVE from a previous year. If we were to find new stuff, that would be forward-thinking research. And up till now, our program here has never made it there. That's like a real PhD level program, where you're actually doing research and finding new things. I've had a couple students find new things because they're way ahead, like Tom found a new jailbreak for the iOS. But that is really quite beyond the level of community college, unless we get very lucky. You have to be closer to the cutting edge to find new stuff. Anyway, what's that? Yeah, no, another one. Yeah, anyway, I think I'll start. Unless there's any more Sam Bowne's going to join. I guess not. Okay. So, what do you have to disable for network fuzzing? Okay, the Nagel algorithm, the thing that makes network traffic efficient by delaying some packets. You can't have that. What kind of exception is most likely to be exploitable? Access violation, because that sort of implies that you managed to change something like EIP. All right. So what technique makes it easiest to determine whether a flaw is reachable? All right, fuzzing will only find reachable flaws sort of by definition. All right, and what operation causes it to wait for the server to send a prompt? Okay, that's read line, of course. Same sort of thing you'll see in Python. All right, so I see a few winners. 2 names are actual names, and then there's that who will have to tell me who they are if they want to get their points. And that's it. I'm just going to clean up here and go up to the lab. I'll do a bit more of this next week. Is someone going to come in on the chat and tell me about bet, or is it bet in the room? Going once, going twice. Bet is not going to get their points, I guess. Farewell.
There's a little delay. You should wait.
I haven't ended it yet. Didn't your chat. Hey, did I miss the 127? No, there's no message. So I think there's nobody. Okay.